Hi everybody and welcome to another lesson with Mrs. John. Today's lesson is going to be about energy transformations. So as you know from the law of conservation of energy, that energy can neither be created nor destroyed, and all that happens is that you can change energy from one form to the other. However, the total energy at all times remain the same. Now in the last lesson you did some questions on energy conservation where something was dropping from a height and all the energy it had at the top was gravitational potential, and then when it falls down all the energy is converted to kinetic energy. So the total energy at the top equals total energy at the bottom. Now what really happens in real life is when something's falling through the air, there is air resistance. So some of this energy, this gravitational potential energy that something has when it's at a height, as it falls down through the air, there is air resistance, friction. So some energy is converted to heat because of this force of friction. So the total energy is the same, but the total gravitational potential energy is not going to be the same as the kinetic energy at the bottom. And often the kinetic energy at the bottom, the total kinetic energy, is going to be slightly less than the gravitational potential energy it had at the top. And those are the kind of questions that is there on this page on energy transformations, and today's lesson is about this. But before we do that, there's something that's not here, and that is, how do we write an energy transformation equation? So for example, so this is the first thing I'm going to tell you. So these are called energy transformation equations. Okay, let's come up with the scenario. For example, if you have a wind-up toy and you wind it up and you let it go, so the toy is going to move forwards, right? So the energy transformation that takes place, we're only going to say about the main energy changes that take place. So over here, when you're winding it up, the toy will have elastic potential energy. So we just name the energy forms, and then we draw this arrow to say that this energy at the start has been converted to many forms, and then we name the forms and we just put a plus sign between the forms. So the main form of energy, because it's moving, would be kinetic energy. And this board is short, so I'll just continue it over here. Plus some energy is lost as heat due to friction, and probably there's some sound energy too because of the noise. Okay, so that's how you write an energy transformation equation, and this was for a wind-up toy. Okay, now suppose it is a washing machine where you put the switch on and the things move. Okay, your clothes are getting washed. Now that needs electrical energy, right? So for that one, the way that I would write is, this is for the washing machine. So you get electric energy. I know it's electric potential, but I'm just going to write electric energy is converted, because the things are moving, drum is spinning, is converted to kinetic energy. This is the main form. Maybe some heat and some sound as well. So in all forms of energy changes, in reality, some energy is always converted to heat. And because it's not a usable form, the term that we use is lost. So we say some energy is lost in the form of heat. So based on this knowledge, let us solve some of the questions that's over here. So I'll work through one question, and then with you, I'll talk you through it. So you should be able to do all these questions on this page. There are 6 of them. Okay, try and work your way through that, and I'll work through these answers as well. Take a photo and load that for you to refer to. So let's look at the first question. So it says a rock of mass 12 kilograms breaks off from a cliff face and falls 20 meters. So I'm just going to write what we know. So this is question 1. The mass of the rock is 12 kilograms, and the height of the cliff from which it falls is 20 meters. So we know these two, okay? Now, what we have to calculate first is because it's at a height, you know, the sort of energy it has at a height is gravitational potential energy. So the first question is, what gravitational potential energy does the rock lose? It loses gravitational potential energy because it's falling down, okay? So the way we write that is gravitational potential energy lost, GP is gravitational potential energy, and the formula for that is EP lost is equal to mgh, or your EP lost is equal to, my mass is 12, my g is 10, acceleration due to gravity, and my height is 20. So I get 2400 joules. Okay, so when you multiply all that, that's the answer you get. Then, what is the main form of energy into which this energy is changed? So the main form, because it's falling, so your main form of energy into which this is changed is kinetic energy. Okay, and question C is, if the speed of the rock when it hits the ground is 18 meters per second, what is the kinetic energy of the rock just as it lands? So you've got the speed. Speed is 18 meters per second. We know the mass. Mass is 12 kilograms. And the formula for kinetic energy is half mv squared, or my kinetic energy is half is the same as 0.5. My mass is 12 and my v squared is 18, so it's 18 squared. So my kinetic energy works out to, and let me just put this in my calculator. So that is, so 1944. So I get 1944 joules. So look at these two numbers. So yesterday's we had them the same, right? We don't have to calculate, but look what's happened today. Okay, so in reality, some energy is lost in the form of heat. And so D, the kinetic energy it gains, is not equal to the gravitational potential energy it loses, suggest what may have happened to the difference in energy. So the difference in energy has been lost as heat due to friction. You've got to say all those words, heat due to friction. And it's not asked in this question, but it's asked in some of the later questions, how much of energy has been lost in the form of heat due to friction? And the answer to that is energy lost as heat is just the difference between these two. So you go 2400 minus 1944, and how much do we get? 2400 minus 1944, and we get 456 joules. Okay, so 456 joules. Now you'll notice that when you're checking the answers are all given to two significant figures. So this is what we do in physics. We look at the numbers given in a question. So these are the numbers that we use, and the number of significant figures is 2. So your answer should reflect that accuracy in which the numbers are given in the question. So we can actually write this answer as 1900, but when I'm doing my calculations, I have to use the unrounded numbers, otherwise I'm going to get wrong answers. Okay, and this 456 can be written as 460 joules. So you always write the unrounded answer, and then under that you can write the answer correct to two significant figures. We don't give answers to one significant figure, it's usually 2 for year 11. Okay, so I hope that made sense. Bye for now.